Okay, so how to determine the vacancy formation energy and atomic migration energy in FCC through the vacancy mechanism diffusion process? How to do that? How to measure that? Design experiments to measure that. So the concept will be that in order to determine the vacancy formation energy and migration energy, first thing come up from your mind will be vacancy. Are there any information related to you can measure or determine whether the vacancy number or concentration of vacancy change in your materials? Can you do that? Or any idea about that? Yes, you learn that when we learned that before, right? At the thermal equilibrium condition, the vacancy concentration, we can calculate the vacancy concentration, and this will be highly depending on the temperature and vacancy formation energy. So in order to determine the vacancy formation energy, first thing come out from your mind will be these equations. As long as we know, and we also can measure the vacancy concentration by several approach, right? But here, when you increase the temperature, you can expect the vacancy concentration increase in the meantime, and there's a vacancy formation energy term inside here. So G can separate into H minus Ts, so you got this relationship. And XV is a fraction of vacancy, so as long as we can measure the NV, and we also know the N, then you can get the XV, right? So this is what we learned in previous slide. But don't forget, we want to measure, right? So something you need to measure. So based on this equation, we know when you increase the temperature and the vacancy numbers, for sure it will be increased, right? So next will be how to measure the NV. Some people probably will think about, oh, professor, can I use the SPM, STM to estimate, to count the vacancy concentration in my materials? Probably. Probably yes, but don't forget, if the SP and STM will focus on very small, tiny region, partial region inside your materials. So the results, the numbers of concentration vacancy, the value for this one is not exactly correct. So first thing come out from my mind will be, is that possible to measure that in micro or macro scale? Then I have chance to say, oh, this concentration is the overall results, right? So here I introduce you the other approach. You can think about that in your mind. In order to get the XV, and I also know the XV is temperature dependent. So the vacancy numbers also can be, when I try to heat materials up, I can see the thermal expansion of these materials, right? So I can measure I use a ruler or caterpillar to measure the delta L over L. This is come from the thermal expansion experiments, right? When I heat materials up, I can observe the thermal expansion, right? But this thermal expansion is not only can contribute from two sources. The first one is probably due to from the lattice constant increase due to the temperature increase, the increase in temperature. So this is so the thermal expansion. When I heat materials up, I can observe the thermal expansion probably still come from two sources. The first one is the increase in lattice constant, and the second thing is come from the increase in the numbers of vacancy or concentration of vacancy. So when I minus the contribution from the increase in lattice constant part, the rest of part will be equals to, it's come from the increase in vacancy, the numbers of vacancy. So I use this term to minus the increase in lattice constant part. And this is one dimensional, right? And the vacancy, the increase in vacancy of a refraction part will be belongs to three dimensional. So I times 3 to represent it. So before we move to the results of the measurement, so I'm going to give you a quick review regarding to the increase in lattice constant. Okay, and the lattice constant part, the increase in lattice constant, you can measure that from the shift in XRD. Okay, so let's give you a quick review to explain why when you increase the temperature, then you can observe the lattice constant increase in the meantime. So this is, as we mentioned before, is a classic harmonic oscillation model. You can see that there's two atoms and contact with a spring and with a lattice constant K, and this with a spring constant K, and this K is related to the bond strength, bond numbers, as I mentioned before. Okay, and this is the vertical axis is energy, and the horizontal axis is the internuclear distance between these two atoms. We call it R. Okay, so when we observe this is a classical harmonic oscillation, you check the energy curve here in showing in green. When we increase increase energy from 0 to 6, increase energy, and we can observe for n equals to 0, you can see that the R will be oscillate from here during the oscillation model, right? But when we talk about the lattice constant, A is related to R, right? Usually we take the average, will be the center of this vibration displacement. So when based on these results, we can take the center for when we increase the energy. So you can observe the lattice constant, or R, does not change with increasing energy. So which means in classical harmonic oscillation, when you increase the energy, you cannot observe the increase in lattice constant. But this is not correct, right? So following, let's modify law or principle we call the Mohs principle. It tells you that the energy curve will be exactly energy curve is not the symmetric one, it's a symmetric curve shown in blue line. So here we can see that when you increase the energy, then the lattice constant increase in the meantime. So this is the quick review regarding to the change in lattice constant as a function of temperature. Okay, so now we know as long as we measure the change in length in macro scale minus the change in lattice point or lattice constant measured by XRD, then times 3, then you can estimate the XV. So let's grab the data published in 1916, and as I mentioned, he measured the alumina. So he has a alumina line or bar here, and he tried to increase the temperature and plot the delta L over L and also delta A over A here. And as you expected, when you increase the temperature, you can observe the delta L over L and delta A over A increase in the meantime for both curves. But in the lower temperature, the curves are identical. But when the temperature above like 516 or higher, you can see that delta L over L is larger than delta A over A. So under these situations, you use this delta L over L minus delta A over A times 3. Then you can get the value at different temperature, right? You can measure this value at different temperature. For example, like you can check that for different temperature. And after fitting, he got this results, and also can separate into temperature independent term and temperature dependent term. And inside this dependent term, the upper portion is the vacancy formation energy, right? Compared to these results. So some people probably will ask, Professor, how to get this fitting? For example, like you have you directly take a log and plot this value versus 1 over t, then the slope and the intercept. The intercept is this term, and the slope will be minus vacancy formation energy divided by k. Then after fitting, you know the value times the k times the negative term, then you get the vacancy formation energy. Okay? So this is what the story goes on. So now you know the vacancy formation energy by through your measurement. Then we know this one, right? But how to get the migration energy of the atom? There are two things come up from your mind. Either you can ask yourself, can we directly measure the migration energy of these diffusing atoms, or what? Oh, because we already know vacancy formation energy. Oh, probably we can measure the E. Then as long as we know the E minus vacancy formation energy, then we can get the migration energy. There are two approaches, right? But as you know, it's very difficult to measure the atomic migration energy directly. So here, we try to measure the E first, then get the migration energy. So based on this equation, how to get the E? Any idea? The way would be, I can measure the self-diffusivity of the diffusing atom at different temperature. For example, like 200K, 300K, 400K, and 500K. Have different D star, right? And take the log D, plot the log D versus 1 over T. And the slope will be, from the slope you can get the E, and from the intercept you got the log D, you can get the D0 star. So this is the story goes on. So we want to determine the total energy delta E by plotting the log D over versus 1 over T. Then you can get the vacancy migration energy. So this is the full story. Okay. So today we ended here.